Everyone, welcome to my short presentation on the homework 1, and my title is Beautiful Mathematics Curves in Polar Coordinates. So I'm Jens from National Taiwan University, Department of Electrical Engineering, and today I'll be demonstrating how mathematics creates art through interactive visualization. We'll explore rose curves, butterfly curves, and other fascinating mathematical patterns. So first, let me explain our setup. We're importing the 4 required libraries as specified in our homework assignment. The key libraries are NumPy for mathematical computations, Matplot library for plotting, Pandas for data handling, and Seaborn for enhanced visualizations. Additionally, we are using Generative to make our visualization more interactive. So now let's dive into rose curves. Okay, so these beautiful mathematical flowers follow the equation of r equals to a times sine n theta, or r equals to a times cosine n theta. The magic happens with the parameter m. When n is odd, we get exactly m petals. For example, 7, we get 7, 1, 2, 3, 4, 5, 6, 7, 7 petals. When n is even, like 4, we get 2 times m petals. So for the blue one, we get 1, 2, 3, 4, 5, 6, 7, 8 petals. So watch how changing these parameters will create different flower patterns, and we will show it in later gradual visualization. The second one is called the butterfly curves. The butterfly curve is one of the most mesmerizing mathematical curves. Its parametric equation involves exponential here and trigonometric that's sine and cosine functions combined in a complex way. So when you see the visualization, just notice how the curves create the distinctive butterfly shape with intricate wave patterns. And in the end, you can adjust the scale, rotation, and detail level to see how these parameters affect the visualization. The third plot is the cardioid or heart curve, follows the elegant equation r equals to a times 1 minus cosine theta. This curve is actually a special case for so-called epicycloid. It's a path traced by a point on a circle as it rolls around another circle of the same radius. So you can see how changing the size parameters later and colors create different heart shapes. The fourth plot is spirals. Spirals are everywhere in nature, from Nautilus shells to galaxies. So here we represent the Archimedean spiral. The Archimedean spiral has constant spacing between arms, while the other spiral, like the logarithmic spiral, maintains constant angle. So and the third one, Fermat spiral, appears in sunflower seed arrangement. Okay. Now we venture into 3 dimensions. These surfaces showcase advanced mathematical concepts. The twisted torus combines rotation with sinusoid variation. And for later we'll see the Klein bottle is a fascinating non-orientable surface. It has no distinct inside or outside. And of course, the Mobius stripe is another non-oriental surface with only one side and one edge. So we'll show our visualization here in the end. The above is a code, so we'll see the gradual curve. So we quickly review the curves we had. So here you can adjust the number of petals and the submit. For this case 7, so it has 7, and if you set it as 6, well, it should have 12, right? And you can adjust also the amplitude. It's basically adjusting the parameter here, 2.4. For butterfly curve, you can set the scaling factors and can see the parameter changes accordingly in the graph title. And of course, you can set the rotation and some detail levels here. So you can see how these parameters affect the actual curves on the graph, and where hard curve is relatively simple and only one parameter to be exact. But you can also change the colors here, and the spirals, Archimedean, which should have equal spacing. You can design the number of turns you want here, like 4.5 or even more, like 10. But make sure Archimedean has equal spacing. And spacing, you can decide the spacing is the parameter here. Okay, sorry, I don't know how to pronounce it. Logarithmic, right? Logarithmic has the same angle between each arms, and of course you can decide the number of curves here. Okay, format. Okay, and lastly we have the 3D surfaces, twisted torus. Of course, the color map is just deciding which color you want to present your surfaces. The climb bottle, of course. Okay, plasma. Okay, this is much cooler. Of course, the Mobius one. Okay. And in the end, you can select Least tab to show all these graphs in one glance. Okay, of course it can clear all of the output and regenerate. Of course. So if you want to play with this interface, you just execute this code, and the gradual GUI will represent here in the output, and you can just modify the parameters and for each graph. And of course, you want to see the overall graphs in one site. You can just switch to the last tab, and that's it. That's my first homework for representing these graphs on Colab. Thank you.